So dynamic programming is it's a really big concept, and we're not going to go over all of it in this one video because that would be impossible. But I do want to give you a nice general introduction to dynamic programming, and again, Fibonacci is a typical way to induct people into this new topic. Now, if you had seen my recursion video, which I highly recommend you go look at that, okay, recursion came out earlier this week, and we talked about Fibonacci using a recursive algorithm. We ran into some limitations with the recursive algorithm, though, because especially like with Python, we were only allowed so many recursive calls. It took up a bunch of memory. There is a much more optimized way to find Fibonacci numbers, and we're going to use dynamic programming. Now, with recursive, the way we kind of did things was, right, we said, okay, cool, I want to find f of 4. All right, well, if you want to find f of 4, you're going to need to find f of 3 and add that to f of 2. Okay, but I don't know what f of 3 and f of 2 are. Okay, well, f of 3 is f of 2 plus f of 1. And then f of 2, right, is f of 1 plus f of 0. I'm going to do that a little bit better. All right, so as you can see, we kind of built out this tree, and essentially we started at the top and said, I don't know what this is. Let's break it down into two subproblems. I don't know what these are. Let's break it down into two subproblems. Then we get to our base cases, right? So we get to our base cases. Awesome. The things we actually do know, because we know that the first number in the Fibonacci sequence is going to be 1, and the second number is also going to be 1, because we said so. And then from there, we build. Now, here's the thing. This is not very natural for human beings, right? If I asked you, hey, Bob, figure out what the Fibonacci number of 10 is. Bob isn't going to be like, well, 10 is the Fibonacci of 9 plus the Fibonacci of 8, which is the Fibonacci of 8 plus the Fibonacci of 7, which is the Fibonacci of 6 plus the Fibonacci of 5. Like, no one's going to do that. Like, no one's brain, at least no one I know of, their brain works like that. Human beings work a little bit differently, right? They don't work in this top-down tree structure in terms of thinking of a problem. Human beings start from what they know, right, the bottom, and they work their way up, okay? So I know that the first numbers are 1 and 1, so then I get 2. 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 3 is 8, okay, and so forth, right? Human beings would start with what they knew, and then they would calculate everything up to whatever their target was. Like, let's say this was the target, and say, okay, cool. That's, to me, mentally, is a lot more comfortable for my mind to kind of think about. With dynamic programming, that's kind of what we're doing. Dynamic programming is all about computing what we know first. Start with the base case. What do we actually know about the problem? In this case, I know the first two numbers of the Fibonacci sequence. No calculation necessary, no special tricks. I know what they are. And then I'm going to start from what I know and build up, okay, to what I want to get to. This is called the bottom-up approach. And what you will find is that in reality, the bottom-up approach is going to be way more efficient in terms of time and in terms of space. Okay, recursion takes up a lot of memory, all right? And it also can have, like I said, Python only allows so many recursive calls and things like that. Instead of doing all that, right, instead of having all these spinning plates, let's just start with what we know and build up to what we want to get to. It really is just that simple. Most dynamic programming problems boil down to that, right? They just basically boil down to start with what you know and build up to where you want to be. And the thing is how do we build up to that? So here, if we think about it, right, each number is just basically the previous number. So what I want to do is I want to start from, let's actually move this around a bit. Let's get rid of some of this stuff. I'll get rid of all this. Okay, so again, what we want to do is we want to basically say, okay, we'll loop, right? We'll start here and we'll loop. We'll start basically at this point and we'll just start doing a loop. We're going to do this iteratively. Okay, we'll get 2 and then we'll move over and then get 3 and then we'll just do this iteratively. We also can still use some of the techniques that we learned earlier with recursion where we can still cache things. So for example, let's say we're at this point now. So let me actually get rid of this arrow so that we're nice and clear. Let's say we're here, right? Well, how did we get here? Well, we already knew these two ones, right? So we knew what f of 0 is equal to 1. And f of 1 is equal to 1. But to get to here, we had to also get f of 2 and f of 3, right? So f of 2 we know is 2. And f of 3 we know is 3. All right, so now we're going to do f of 4, right? Well, f of 4 is f of 3. So f of 4 is equal to f of 3 plus f of 2. Well, my guy, we already did the work for this, didn't we? We don't need to recalculate these things. What we need to do is we need to remember we have that cache, that like notebook, where everybody writes their work in, and hey, go check the notebook. Do we already have f of 3 and f of 2 written down? Yes, we do. Then don't recalculate them. Just go grab them from the clipboard, put them in, add them together, we get 5. Bam, now we're done. Okay, so memoization, being able to cache previously computed values, is still very much on the table here. So again, the little technique we learned last time will come to here. It's that this time we're going to do this, I think, in my opinion, the more natural way. All right, let's look at how we would actually code this. Hi, my name is Jonathan Hopp, and if you're enjoying this tutorial, I invite you to visit my website, codingyourcareer.com. I've got courses on Java, JavaScript, TypeScript, and all of the famous frameworks like React and Angular, the kind of things you'll need in order to break into the world of tech and get the knowledge that you need. It's even great for people who are already in tech and want to level up their skills. So it's codingyourcareer.com. Let's continue with the tutorial. All right, so the biggest thing about dynamic programming is that it feels similar to recursion, but actually it's more like the opposite direction. So with recursion, I basically said, hey, I would like to figure out what the Fibonacci number at 10,000 is, which is, some gigantic number. And then, okay, cool. That means that I need to break that down to 2 smaller subproblems. 9,999 plus Fibonacci 9,998, and then down and down it goes. With dynamic programming, we're starting with the simplest cases, which is the first Fibonacci number is 1 and the second one's 1. And we're going to iteratively build up. We're going to do a bottom-up approach. And a lot of times the bottom-up approach is a lot more efficient, especially in terms of time, in terms of space. It is usually more efficient. One of the things, the problems we ran into in the recursion video, so if you don't understand what I mean by recursion, I do have a video on recursion. You can go take a look at it, and I talk about, we actually work out Fibonacci using recursion. In recursion we came up against a hard limit. We couldn't, for example, do above 999 because Python will only allow us to make up to 1,000 recursive calls. So then what happens when we want to figure out the Fibonacci number for a super high number? Like 10,000 actually isn't super high, but with recursion we couldn't do this. So with dynamic programming we will be able to. All right, let's start this off. So if num is less than or equal to 1, we return 1. There's no reason to calculate this. If you just give me 1, bam, there you go. All right, we're still going to use a cache. We're still going to memoize things because if you think about it, it doesn't really matter that I'm doing dynamic programming. I want to be able to, if I've already figured out the answer to the problem, don't figure it out again. There's no reason to do that. So what I'm going to do is fib cache is equal to, and I'm going to put in what I know first. All right. Now, if you're new to Python or don't know what this means, this is a dictionary, and it's just basically key value pairs. The key here is 1. The value here is 1. The key here is 2. The value here is 1. All right. And why is that? Because the first 2 numbers, the number in the first spot and the number in the second spot are both 1, because that's the way Fibonacci works. Everything else just builds off of that. And by the way, the reason I like dynamic programming is also because it feels very human. Like if you ask a person to figure out the Fibonacci sequence, what they would do is they wouldn't just Jonathan, what's the 10th Fibonacci number? I wouldn't just be like, oh, the 10th Fibonacci number is the 9th and 8th, which is the 8th, the 7th, and the 6th and the 5th. No one thinks like that. A person is going to start off with 1 and 1 and build up to 2 and then go to 3 and then go to 5. You see what I'm saying? So this, to me, feels a lot more natural. So, also, we're going to do this iteratively. So iteratively is kind of your signal word for we're going to use a for loop. For I in range, and we're going to start off at 3, and we're going to go to num plus 1. Again, if you're not up on your Python, no big deal. this is a for loop that starts off at 3 and goes up to, but not including, num plus 1. That's what range does. So that's all this is a for loop. And you can do this for loop in whatever language you're most comfortable with. All right? We're going to say our cache at num is equal to fib cache at I minus 1, which is the previous number, plus fib cache at I minus 2, which is the number previous to that one. So again, the algorithm is the same in terms of we're adding the two previous numbers, but we're also checking the cache for those. And the cool thing is that we start off with the base cases, so everything will be built up from that, and our cache will slowly grow, right, as we iterate through more numbers. So what I want to do is I want to just kind of help you understand that. So for example, we're starting off at 3, right? So fib cache at, let's say, like here. Oh, actually, my mistake. This should be fib cache at I. Just realized that. Sorry. Fib cache at I, which is 3, will be equal to fib cache at 3 minus 1 plus fib cache at 3 minus 2. Well, we know what fib cache at 3 minus 1 is 2. We know what that is. Fib cache at 3 minus 2 here. We know what that is. So we'll cache both of these. We'll cache fib of 3 and move up from there. Then I will become 4. All right. Then that becomes 4 minus 1 and 4 minus 2. Right? As you can see, what 4 minus 1 becomes 3, which is already in the cache. So we kind of saved ourselves some trouble. All right. So as you can see, as we go through, the cache becomes bigger and bigger, and we just have to do less work. All right, so sorry about that. This is supposed to be I here. All right, so fib cache at I equals fib cache at I minus 1 plus fib cache at I minus 2. And all we got to return after that point is basically, you know, the number we're looking for. All right, moment of truth. Let's see if this blows up. Let's see if this cannot take a number this big. All right, so I have no idea what this number is. Like, it is beyond my comprehension as a human being, but there you go. That is the 10,000th Fibonacci number. And as you notice, like, we were able to do that. I could not do this with the recursive implementation of this. It was impossible. Now, let's analyze the time and space complexity. So, remember, time and space complexity is all about, as my algorithm grows bigger and bigger and bigger, right? What's the difference in time? Like, how much relative time am I taking for each new unit of work, right? So you could think about it like, it takes so long to figure out the 10,000th Fibonacci number. Compare that time to how much it takes to figure out the 10,001st Fibonacci number. Remember, it's the difference in the time, all right? How much time it took you to get from one to the next. All right, and compare that to how long it take you to get from 10,001 to 10,002. So it's all about relative time. It's that change. Okay, if you're into calculus, you might understand like limits and differentials and things like that. But basically, the way I look at it is essentially if I, just take it up by 1, right, and take it up by 1 again. What's the kind of the ratio? How much extra time am I taking? This is linear. So essentially, we're doing a for loop, right? And so like the time it takes to do 10,000 versus 10,001 versus 10,002, that time, the unit of time, is going to go up constantly. Well, Jonathan, we're caching things, right? Yeah, so we're caching things. So we're kind of like lopping off some of the work that we would otherwise have to do, which is nice. But again, we're talking about as like X is a million. X is 10 billion, 10 trillion, 10 quadrillion, right? So the number gets arbitrarily large. So caching, while it definitely makes a difference, right? On the whole, we kind of look at this as linear, all right? Just the general trend. Now, what about space complexity? How much memory are we taking in comparison to how big the, bigger inputs, how does that affect memory? We do have this cache, which is going to get bigger and bigger and bigger as the number grows bigger. So because we had to save all of our pre-computed values. And so this is also going to grow linearly with the algorithm as a whole. So we're going to have to take memory up in order to perform this. Now, what if I told you we actually don't need to have linear memory? What if we can have the memory be constant? Meaning, no matter how big of a number the person wants to find the Fibonacci for, we will use the same amount of memory. It's totally possible. And I'm going to show you the optimization a little bit, but what I want you to do is I want you to think about it, okay? Put your thinking cap on, and how could we, like, do we really need this dictionary here? Do we really need to have a key value pair system to actually keep track of the information that we need, all right? Because if you think about it, once we get the Fibonacci of, like, I don't know, 800, think about that, right? Once we get the Fibonacci 800, Fibonacci of 2 and Fibonacci of 4 and Fibonacci of 50, they're not useful, right? Like, I don't care what, like, if I'm looking at Fibonacci of 800, the only thing I really care about is Fibonacci at 800 minus 1, right? And Fibonacci at 800 minus 2 at that point. All the previous stuff that's beyond that range at this point in time, I don't care about. So we don't really, if we could find a way to not have to use this hash map, this dictionary, we could save ourselves a lot of space, because there's a lot of space that we really, ultimately speaking, at any given point don't need. All right, so I want you to think about it, pause the video, give it a whirl, all right, and then after we come back, I will show you the answer. All right, so I said that we could do this problem without having to use this dictionary. It's not necessary. And we could actually do this in constant memory, meaning that doesn't matter how big of a number that we pick to find the Fibonacci number for, the amount of memory we're using is going to basically be like nothing compared to that. It's not going to really change at all compared to the change in our number. So what we're going to do is we're actually going to replace this dictionary. It's going to get rid of it, and we're going to actually use variables here. So we're going to use previous and current, and we'll make them 1 and 1 respectively. Now, if you don't know much Python, you don't really need to. We're declaring variables, and we're saying previous is equal to 1 and current is equal to 1. All right, that way we can kind of save space. I don't have to write them on 2 different lines. That's all it really means. So we'll do a for loop. I don't need to keep track of I, so I'm just going to use this placeholder underscore. And we're going to start off at basically 2 and go up to the number we're looking for. All right, now what do we do from here? The previous number and the current number. Okay, previous is going to be equal to current, and current will be equal to previous plus current. What the heck does this even mean, Jonathan? All right, so what this basically means is that really, as long as we know the first 2 numbers, we only ever really need to know like the current number and like the previous number to calculate, to keep the train running, basically. What the heck are you even saying to me, Jonathan? All right, let's kind of work it out from here. All right, we're starting off at 2, right? So we're going to go up from 2 up to number. All right. We use a comment to help you keep track. Previous, all right, so previous right now is 1, and then current right now is 1. So let's do the first iteration. The first iteration says that previous becomes current, so previous is equal to 1. All right, so that's what you need to remember here. We're just previous is equal to current. That's what this basically means. All right, and then what about current? Well, current, right, becomes equal to the previous number plus the current number. Well, they're both 1 right now, so current will become 2. All right, that's after the first iteration. Let's go to the next iteration. All right, previous will become current. All right, now this doesn't happen in order. It just basically happens all at once. So you could think about it like that from that perspective. So like don't get too confused with this part. Like previous, when this evaluates, previous will still be 1. So current was previous, which was 1, and then current, which was 2, right? And then so that becomes 3. So there we go. So previous becomes 2, current becomes 3. Next iteration, previous becomes current, right? Becomes 3. Then previous, which was 2, and then current, which was 3, becomes 5. So you see how this is working? We're just using these variables, right, to hold the previous number, the current number. That's all the information we really need to go to where we want to go, because we had the first 2 numbers down. We knew what the first 2 numbers were going to be. Now, you may be saying, well, Jonathan, you said this was constant memory, right? And if we have Fibonacci of 1 billion, right, then the previous and current are going to be like these huge numbers. And those numbers are going to be really big, and so a big number is going to take much more memory than like a number like 3 or 5, right? So 3 or 5, 7, 8, they take so much memory, but a billion is going to take up more space. So how could it be? You can call it constant. Again, it's relative. I can pick basically any arbitrarily large Fibonacci number I want to find. And if you think about it, the relative change in the amount of memory I will need is not going to be that much, because I still only have two variables, right? And so they may take up a little bit more space, but that change in comparison to the change in the number is very small. Okay, remember, we're looking at, like, as the number grows bigger and bigger and bigger, is there much change overall? And the change in memory is not going to be that much. I basically just have two variables. They'll get negligibly bigger as Fibonacci gets bigger, and that's about it. All right. So in this case, we sort of approximate that to constant. So this will get the job done again with much less space. Again, I will run it, and oops, we got to also return the current number. So we actually have something to print. And then if I go ahead and do it, I get that large, ridiculous, like, huge number. God knows what this is. All right. So good on Fibonacci. All right. So this is, like, the most optimized for both time and space. But as you can see, dynamic programming kind of helped us to do this in a much more efficient manner. Again, because we're doing bottom up. And a lot of times, especially when you're doing coding problems, you're trying to optimize things, doing things bottom up is better. Okay, recursion requires the computer to hold a lot of information at once. Basically, it's because you're, like, waiting for sub problems to be solved. The computer has to keep track of all the sub problems waiting to be solved. Whereas with dynamic programming, you are starting from the bottom and building up to where you want to go. So the computer only ever has to keep, you know what I'm saying? The computer does not have to keep a bunch of stuff, a bunch of spinning plates going. It just says, okay, cool, I can keep track of where I am, where I used to be, and then keep a rolling tabulation that goes by. So, and a lot of times dynamic programming comes out to be a lot more efficient than, like, the recursive version of it, if recursion can be used to solve the problem. Well, hopefully this, again, dynamic programming is a huge concept that by no means was this video aiming to even go over every single little thing in dynamic programming. There's tons of other problems we're going to do over in the future. But the main idea, again, is let's start with what we know and build up to what we want to know. Whereas recursion was, what do I want to know, and break it down into smaller problems till we reach the simplest problem, and then it will bubble back up. All right, those are kind of the two conceptual ways to think of recursion versus dynamic programming. And as we do more data structures and algorithms, you'll start to get a better appreciation. But hopefully, if you're new to dynamic programming, you're new to data structures and algorithms, hopefully this was a gentle and easy to understand introduction to what you're going to be learning much more of. All right, thank you for watching. As always, like and subscribe. Visit codingyourcareer.com, where you can look at other videos that are just like this about various different topics, and I'll catch you next time.